Okay, so welcome back to the lecture number 8 of this particular course. Last time we saw how to do the coordinate transformation, and let me just take you through the same. And then before that, we tried to get into this ionic activity and try to derive the activity coefficient using Debye-Huckel equations. So we just about started on that after essentially completing the grand plot scheme of calibration and measurement of electrode. So the coordinate transformation was needed because we were trying to illustrate or we are trying to find out mathematically the potential function. So essentially we use the Poisson's equation, which is essentially a spatial derivative of the potential function, and equated that to the charge density 4 pi rho by d. And we also figured out that because we are talking about a spherical central charge of interest and an ion cloud around it, we would have to deal with eventually with a spherically symmetric situation that will make our life easier. And so therefore we made a coordinate transformation of Cartesian to spherical. And in this case we illustrated how we can find out this x, y, z, the point on the top of this radius vector with respect to r, gamma and theta, gamma being the angle between the projection of the radius on the xy plane, and theta being the angle between one of the axes, in this case the y axis, with this projection vector on the xy plane. Okay. And so essentially do the coordinate transformation, and I would expect the students to actually go do and do this as a part of the homework assignment that will be eventually given. So if we consider the whole distribution and also consider spherical symmetry, okay, that means no variation whatsoever with gamma or theta. Okay. So spherical symmetry, as if these potential functions are like shells around the small charge of interest, positive charge of interest. In that case, the final equation boils down to 1 by r square partial with respect to dr of r square partial of phi with respect to r. Okay. And this can be equated to minus 4 pi rho by d. All right. So that is how the Poisson's equation can be written down, assuming spherical symmetric, assuming spherical symmetry. So essentially the potential function's variation is purely with respect to the radius vector r in that case. So this can further be kind of expanded into by putting the value of rho that we obtained earlier in terms of the subscript I and the total number of charges on the point A as minus 4 pi by d Ni Zi square epsilon square phi by kT. All right. And this is essentially from 1. Okay. So we had assumed this in equation number 1 in the earlier presentation. So now let us make some presumptions here. We just for the sake of convenience assume a factor k, and this is actually this k is different than the Boltzmann constant k, and actually let us in order to just make it a little more simplified and without any problems, let us consider this to be small k. Okay. So written like this, small k. So we can rewrite this equation as 1 by r square d by dr r square d phi dr to be equal to k square phi. Okay. Small k square phi, that is what we would be trying to look at. Okay. So let us just convert this into small k square phi. Okay. So what is k square then in that case? K is essentially a parameter which is equal to minus 4 pi, or it is equal to 4 pi by d epsilon square by k t, okay, where this k is the Boltzmann constant, okay, sigma n I z I square to the power half. All right. Let us actually write this as equation number 2. It is very important because later on we have to write the final formulation in terms of the subscript I and the various other parameters which are included in this small k constant. All right. Let us call this equation 3. All right. So, if you go through PDE's partial differential equations, again any graduate program on them, there are generalized solutions for representing or finding out the solution for certain kind of PDEs. In this case, the generalized solution that one can think of for equation 3, okay. So, generalized solutions for equation 3 comes out to be equal to phi equals a to the power of minus k r pi r plus a dash e to the power of k r by r. All right. So, a and a dash are constants which we need to ascertain or know, okay. R of course is the radius vector, and k, as we know, is given by equation 2 here. So, one way of checking back whether this is going to work or not is to put the value of phi in equation 3 and see whether you have a equality on both sides, okay. So, essentially if we put this root and try to evaluate the various aspects of the behavior of potential function, that means what we know as boundary conditions of the potential function, we would be able to estimate these coefficients a and a dash. Let us look at it how. So, as we know that at r equal to infinity, at r tending to infinity, the potential function phi would be also equal to 0, okay. That is what the basic premise was when we were talking about a central charge distribution and an ion cloud, that the potential generating from this small ion of interest, positive ion of interest at a distance which is infinitely spaced, would be 0 essentially. There is no potential at infinity. So, therefore, if we assume phi to be 0 at r equal to infinity, and if we know from earlier that the equation for phi is a e to the power of minus k r by r plus a dash e to the power of just k r by r, k r by r, okay. Then the only way you can have this condition r equal to infinity, phi equal to 0 validated is by assuming that a dash is equal to 0, okay, should be equal to 0 for obvious reasons, right, because if r is essentially, if r is give me a minute here. So, if r is infinity, then in that case this particular term here e to the power of k r should also go to infinity, right, and r being infinity, the only way to avoid the situation is by assuming a 0 coefficient, so that there is validation. So, therefore, really phi is represented as a e to the power of minus k r excuse me by r, okay. And as we know from earlier that the rho, essentially the charge density, is also minus a times of sigma n I z I square, okay, epsilon square e to the power of minus k r by k t times of r, okay. So, essentially this is same as writing minus sigma n I z I square e square phi by k t, phi being e to the power of a e to the power of minus kr by r. So, we have just made a slight rearrangement here for the charge density. Okay. So, in other words, you know, this essentially this value. So, you know, if we look at the equation number 2 earlier that we had done before, this in terms of k, how we can represent this whole expression. So, then from there we can easily get that k here, if you look at, has been represented as 4 pi by d epsilon square phi, sorry, not phi, phi is actually outside. Okay. So, k square epsilon square 4 pi by d Boltzmann constant k times of t sigma n I z I square to the power of half. All right. And so, we can do a little bit of manipulation here, so that we can represent this whole term in terms of k. And so, essentially from here we can also have an expression wherein the essentially the epsilon square sigma n I z I square by k t term reduces to just give me a minute here. So, epsilon square sigma n I z I square by k t term, where k here, this k is the Boltzmann constant, kind of represented as d by 4 pi small k square, right. And so, if I substitute that back into this equation 4 here, the final equation that I get is basically minus a times of d k square, okay, by 4 pi, okay, e to the power of minus k r, and of course, there is a r term in the denominator. All right. So, it is basically a k square d, and since this particular term has, you know, this can be, you know, represented as minus a d k square e to the power of minus k r divided by 4 pi r. So, this is an important aspect, okay, because this is essentially what the charge density at point A really is. Okay. And now, we will like to have a look at what is really the corresponding Counterion clouds charge density. So, for doing that, as we are aware that the principle of electron neutrality is always to be followed. Okay. And so, by that principle, we know that the total amount of positive charge in a sense would equalize the total amount of negative charge. Okay. This is a very interesting situation, because we have a case where we have a positive charge here, and there are several minus charges or negative charges in the Counterion clouds here, right. Exactly. So, so essentially the total charge in the ionic atmosphere, let us say all the way up to infinity here, okay, it is going to up to infinity. So, there are charges here, there are charges here. So, there is essentially a whole bunch of these Counterion charges, assuming a single positive charge all the way up to infinity, which would totally be able to balance this particular charge. If we assume that, and if we try to find out what is really this charge density, okay, of the Counterion cloud, and equate that to just the negative magnitude of the positive charge here, we should be able to get an equality between the two. All right. So, let us try and do that, and then with the charge density that we had figured out in our earlier slide, we will try to find out what the coefficient A really would be. Okay. And this is of immense utility for us, as you will see later, because essentially you know, all this ionic activity and ion selective electrodes do depend a lot on how this particular behavior of surrounding ions would be affecting the electrical contribution of the particular ion of interest. In our case it is the positive ion. All right. So, let us assume the central charge to have plus Zi epsilon as the total charge. Okay. So, of course, if I have let us say a positive ion here, and this has let us say some kind of a radius where let us assume that if you have some distance actually at A, which is very close by here, the radius is A, and we assume that there is an ion cloud which extends all the way up to infinity, let us say, but then at a distance r from this center, we are trying to see what is the charge density in a thin shell of the counter ion clouds. Let us assume that this thickness of this shell is as small as an infinitesimally small value of the radius function r here as dr. Okay. So, the total charge that way, if we want to find out, so the total charge of the counter ion cloud would be represented as the charge density times the volume of this thin annular, right, assuming this is a thin annular, spherical annular. So, we need to find out what is the total charge stored in the spherical annular by looking at this volume here. So, we get this as rho times of let us assume that you have essentially a thin ring which you can open and close, and which has a total, let us say. Okay, so basically the volume of the thin annular here is we are talking about is essentially 4 by 3 pi r plus dr cube minus r cube, right. We assume that we are trying to calculate the volume of this thin annular here. So, the radius vector all the way up to here is r plus dr, and here it is r, and so essentially you are trying to create a volume difference. So, let us actually try to look at what this volume would be like. So, essentially 4 by 3 pi, and then we have r cube plus dr cube plus 3 r dr times of r plus dr, okay, minus r cube. All right, these get cancelled away, this is too small a quantity. Okay. And so, essentially if we look at this quantity here, it is 3 r square dr plus 3 r dr square. We assume dr to be so small that even this is neglected. Okay. So, we are left with only pi 4 pi r square dr as the elemental volume here in this particular annular. And so, therefore, if we want to calculate the total charge in this thin annular, it would be and total charge of the counter ion cloud. So, we can actually give a boundary condition here as if the density has to be calculated from the radius of the basic ion A all the way to infinity of this expression 4 pi r square rho dr. Okay. And this essentially is nothing but an integration of the surrounding ions ion density, okay, or ionic concentration. And what this should be equal to really, as I told before, that for the principle of electron neutrality, this should be equal to the negative of the charge as the primary, as the charge of the primary ion of interest, which is a positive charge. Okay. So, essentially from this equation we should be able to get some information about the parameter A, as we had actually defined before while calculating the density rho. Let us look at how we do that. All right. So, essentially rho, again from the earlier equation, had come out to be minus a k square by 4 pi. Give me a minute. So, this k here is a small k. Okay. We should not confuse between both the different k. So, a minus a k square by 4 pi times of d dielectric constant times of e to the power of minus k r by r. Okay, that is what rho is, and we are calculating an integral from a to infinity of 4 pi r square a times of small k square by 4 pi r d e to the power of minus k r. All right, that is what this particular k is really, okay, k r. So, in a nutshell, this is equated to Z I times of epsilon for being electrically neutral, or in the case of electroneutrality. Mind you that this is because this being negative sign, the negative sign on the right cancels because of that. So, let us actually try to integrate this and find out what comes. So, this 4 pi goes away, there is a first power in r which is retained here, and what we are left with is an integral a k square d integral a to infinity r e to the power of minus k r equals to Z I epsilon. Okay. So, we will like to integrate this by parts. All right, and so essentially if we integrate them by parts, we know that between a and b f x g dash x dx, okay, is actually equal to f x g x from a to b minus integral a to b f dash x g x dx, right. I just want to reiterate what integral by parts says. So, essentially here f x equal to a, the f x here is essentially equal to r, okay, and the g x here is equal to e to the power of minus k r. So, naturally this g dash x is equal to e to the power of minus k r. So, therefore, g x becomes minus e to the power of minus k r by k. All right. So, that is what g x becomes, and so therefore, when we are trying to calculate integral a to infinity r e to the power of minus k r, we are essentially doing minus r e to the power of minus k r by k, okay. The f x g x term between a and infinity, b in this case is infinity, minus integral a to infinity f dash x, which is in this case 1 because f x is r, f dash is nothing but d by dr of the function r times of g x, which is minus e to the power of minus k r by k, all right, dr. Okay. So, that is what this integral would be eventually looking like, and on solving these equations, we get so the final value here as a to the power of minus k a by k plus e to the power of minus k, give me a minute, e to the power of minus k a by k square. Okay. That is what the final integral would look like after we put the value of r between a and infinity and evaluate these term 1 and term 2 here, okay, in this particular equation. So, that is what essentially the ZIE would really be, okay, the ZIB would really be. So, starting from here should get an idea of what A would be, okay, because A is essentially in the potential term, and from the differential equation A is essentially also an unknown so far, and we need to estimate the value of capital A, okay. So, essentially this would be the only method of doing that. Let us look at by solving what the value would come out to be equal to. So, we just rewrite this particular, if you look back here, the value of, I am sorry, look back here, the value of a k square d into the integral which we had just tried to find out is ZIE, right. So, this becomes ZIE by a k square d, okay. So, we take this equation at the next page. So, we have on one side a e to the power of minus k a by k, okay, plus e to the power of minus k a by k square, and that is equated to essentially ZIE by a k square d, okay, all right. So, let us take this term here aside. So, we are left with a k square d times of, if I try to multiply this term by k above and below, so that there is a common denominator, we are left with e to the power of minus k a times of 1 plus k a, okay, by k square is Zi times epsilon, and these two go away, and we are left with an expression a equals Zi epsilon e to the power of k a by d 1 plus k a, all right. So, that is what the value of a is, the coefficient a is. Simultaneously, if you look at what phi is, phi was represented as a e to the power of minus k r by r, okay. So, substituting the value here, we are left with Zi epsilon e to the power of k a e to the power of minus k r times of divided by d 1 plus k a small a times of r, okay. So, that is what the potential function phi at that particular point is. So, now we have pretty much everything known. We know what k is, we still do not know what a is, and this a essentially is also known as the ion size parameter, as we look at in the next slide, all right. So, the first thing which comes to our mind is, let us really find out what xi at a is, okay. That is essentially what the potential function at the point a really was, okay. So, if I put the value of a in this particular equation here, all right, we are left with Zi e epsilon divided by d 1 plus k a times of a, as these two terms k a and for r equal to a they cancel out, all right. So, we are left with Zi epsilon by d times of 1 plus k a times of a, okay. So, this gives us an interesting observation. We can try to kind of independently make these two coefficients on two different terms in the denominator, or we can try to solve this particular equation using partial fraction concept to interpret about what is the contribution of the ion in the potential and what is the contribution of the surrounding ion atmosphere, right. Because potential, as you know, is nothing but 1 by 4 pi epsilon naught some charge contribution, let us say q, divided by the radius or the distance of a point from that particular charge. In this case, the distance that we are considering is a, right. And so let us actually split it using partial fractions. So if you try to do that, the phi value can be which is represented as, let me just borrow what I did in the last slide for convenience sense, 1 by a 1 plus k a can be written in terms of partial fraction as 1 by a minus k times of 1 plus k a. Okay. But just compute this. So, if you make this the denominator will come out to be a times of 1 plus k a, and 1 plus k a will be here minus k times of a. So, that essentially this is 1 by a into 1 plus k a. So, this is the correct partial fraction for this expression on the top, and let us split it up into two different terms, z I by d times of a minus k divided by d times of 1 plus k a. So, times of z I e. So, what we are sure about one thing is that this probably corresponds to the contribution from the ion itself, okay, from the ion itself, as it corresponds to an r value equal to a, as we had investigated before, the radius value equal to a, and this should be, because even it is negative, as you can see here, should be the contribution of the ion atmosphere. So, this is a very important fact, that this is a negative ion atmosphere, as we know, right, because the central ion was positive, and so therefore, the contribution to the potential function by this particular term here is also negative. So, the very important factor here then is that the final potential function is not only because of the charge of interest, but also because of the surrounding counter ion cloud or the counter ion charge which is surrounding it. So, so therefore, if we kind of try to estimate what is an average radius or what is an equivalent radius of such a counter ionic cloud, I could write this down very well as z I e by d times of 1 plus k a by k. Okay. So, this is a kind of radius equivalent of a counter ion cloud. All right. So, there is a radius equivalent of a counter ion cloud, and which might mean that that 1 by k 1 plus k a, I am sorry, let me just write this down a little bit again, 1 plus k a by k is the radius of ion cloud. Okay. So, now let us go to another very important aspect, that how we can correlate this to all this information really to the activity of the particular ion of interest, which is a positive ion in this case. Okay. So, basically we would now like to find out how all whatever we have done so far is related to the activity of an ion of interest. Okay. And for that there has to be some kind of a relationship in terms of the amount of work that is done, for bringing a small amount of, let us say, the counter ion cloud from infinity into the center of the counter ion cloud, and try to equate that to delta G equation, okay, the free energy, the Gibbs free energy equation. And but this will be clear in a little bit when I just demonstrate that part. So, let us see, or let us study first that what really would be the free energy involved in all this process, where the ions kind of come from infinity, and they form a counter ion of minus ZIE around the around the main ion of interest, which is plus ZIE. So, how all that happens, and the work done, the amount of maximum work done, which is also equal to the free energy of the system, how that can be defined in terms of the ionic concentration. Okay. So, as we know from before, from the Van 't Hoff equation, while doing electrochemical cells, we found out that the amount of free energy of such a self organizing system would be delta G, would be given by the equation delta G equal to delta G naught plus R times T natural log of activity of the ion, which is gamma I xi, right. If you remember, when we talked about the activity, ionic activity, and in fact when we were discussing the electrochemical cell, we considered that there is a lot of high ionic background, and therefore there is only one specific ion of interest, and so the activity coefficient gamma is 1 in that case. Okay. But in our case here, really the activity coefficient was, so that is why the activity was a function of concentration. Here though, the activity is, because of the several interacting ions that are present in the solution, a finite value gamma I into the concentration of the ith species. Okay. So, we do get a relationship between the free energy associated with this dynamics that is going on around the positive ion and the activity of the particular species of interest. So, let us see what would be needed, okay, to bring let us say a few moles of the counterion cloud from infinity into such a cloud. So, let us say you have a positive ion here, this is the infinite plane probably, and there is a bunch of counterion clouds which are surrounding it in all directions, right. And you have this counterionic radius that is given from the earlier equation by this factor 1 plus Ka by K, okay, as we did in the earlier equation. So, now all said and done, let us say this kind of a charge distribution is existing, and you want to bring some charge, some elemental charge, let us say, and let us also assume that this is minus Zi epsilon. Okay. We assume that this total counterionic charge is minus Zi epsilon. We had made this presumption while deriving this ionic radius formulation, okay, of the cloud. So, we assume that a very small amount of this charge, let us say d Zi epsilon, is being brought in this counterion cloud. So, the amount of work that would be done for such a small charge to get into the counterion cloud of value Zi may be at a point where the potential is also defined by the formulation K Zi Zi epsilon by d 1 plus Ka. So, if you may remember, this was the contribution of the potential from the negative ion, okay, from the negative ion. And so, if you have a potential function somewhere very close to this ion, at a distance say a, where a is the ion size parameter in this case, and you are trying to get this small d Zi charge very close to this point. The amount of work that is done really in this case is nothing but the free energy change of the system, okay. The work that is stored in the system, if allowed, the system can do an identical work, okay. So, let us find out what happens in terms of the total work done, okay. Let us assume this work is dW, and we want to find out the total work done when all this charge, all this Zi is brought near to this point A, okay. So, we can represent this by just a very simple integral dw, and we assume that the dZe varies from 0 all the way up to ZIE phi I times of d ZIE. Okay. That is what the total work done varies. So, this is actually nothing but equal to the amount of work done into the system, done in order to give an ion of potential plus or phi e its charge of minus ZIE or its counter ion atmosphere. Okay. So, the delta G minus delta G naught for concentration equal to 1, which is actually equal to the work done in totality, all right, work done in totality per mole. So, essentially this is for this is the work done in totality. So, this divided by n, the number of moles of charge that is transferred can be equated to the integral dw, right. So, therefore, if we evaluate this integral 0 to ZIE times of phi I, and phi I from earlier thought as basically the counter ion contribution part of the potential, right. So, it is Zi epsilon k divided by d 1 plus k a times of d ZIE. Okay. So far things are pretty clear that we are talking here about trying to give an ion of potential phi I its counter ionic charge of minus ZIE, okay, in bits and pieces of dZIE, and then the total amount of work done is computed by doing an integral as if the counter ion were 0 before and it goes all the way to about ZIE. So, it is a kind of indirect way of looking at it, right. So, this essentially is nothing but this work done in totality by the number of moles, okay, because this essentially is again per ion, this is per ion, all right. So, but delta G minus G essentially is the work done in totality, all right. So, you have to divide this on both sides by the number of moles of the charge that is transferred in order to equalize this work done per ion of interest. So, number of moles is essentially needed to make this work done per ion. So, if you look at the equation for delta G from before, delta G minus delta G 0 really is equal to your R times T ln of gamma I xi, right. And so, therefore, per ion delta G by minus delta G 0 by n should be essentially equal to R by n T ln of, me go ahead and just change this a little bit here. This is ln of the activity gamma I xi, okay, ln of gamma I xi here. So, R by n as we know is nothing but the Boltzmann constant K, right. K is R by n, the Rydberg's constant per mole of charge that is transferred times of K times of ln xi gamma I, and this is equated to our work done here, which is essentially this factor 0 to Z I e, and by the by this is a negative charge. So, it is minus Z I e Z I epsilon by d k times 1 plus k a times d Z I epsilon. Okay. And essentially if you do this integral here, it will come out to be minus Z I square epsilon square k divided by twice d times of 1 plus k a, varying between 0 and Z I e. So, essentially nothing but the same Z I e square Z I square times of epsilon square times of k divided by twice d 1 plus k a. Okay. And this is equated to our earlier stance here k t times of ln gamma I xi. Okay. All right. So, when we are talking about contribution per mole, okay, the xi here can be considered to be for 1 mole. Okay. So, essentially if we look at 1 molar solutions, this can get converted into k t ln gamma I, right. And so, therefore, for a unimolar solution, the relationship between the total work done and the total free energy can be as given in these set of equations. So, from this though we have an important idea of what the activity in such an ion of interest would really be. Okay. And therefore, let us in a little different manner try to see what gamma I is by taking antilogs on both sides and trying to expand this term here on the left into a more appropriate or a more readable term in terms of mean ionic strength of the solution. Okay. So, here we know that K is also 4 pi by d epsilon square by k t sigma n I Z I square to the power of half, right. So, we can do a little bit of change here with this n I term, that if we assume that this C I to be the concentration of the ion of interest, okay, the ith ion of interest, then Ni can be represented as the number of moles in Ci times of so that means the number of this is the Avogadro number, this is the Avogadro number times of Ci divided by 1000. Okay. Ni, mind you, if you would have recalled from earlier, was the charge density. Okay. So, charge per unit volume, and since we were talking about CGS units, so this is essentially charge per 1000 cc or per cc, I am sorry, charge per centimeter cube of volume, charge per centimeter cube of volume. Okay. So, Ci of course is in molarity, which is moles per liter, and therefore, 1 liter is around 1000 centimeter cube, and thus this 1000 term here. So, essentially the number of moles or the number of charges per unit volume can be a function of n Ci by 1000. So, if we substitute that back into this equation here, we can get the value of k as 4 pi by d epsilon square by kt sigma n Ci Zi square divided by 1000 to the power of half. Okay. And essentially we can take we can do a further simplification and try to write this terms in terms of 8 pi by d epsilon square n by kt times of half sigma Ci Zi square whole half. Now, this term is really a very interesting term, and we can also call it the mean concentration, okay, or you can call it the mean concentration in an ionic solution. Now, all said and done, because we have utilized a certain protocol or a certain way of notating the charge Ni to be the charges, the negative charges and the positive charges. Okay. And so, therefore, ultimately if suppose you have a CaCl2 solution where you have a Ca plus 2 as the positive charge and Cl minus as the negative charge, the equation that you are finally going to derive out of all of it where it can report about the activity should take into consideration, because it is a different valency situation. Ca has plus 2, Cl has minus, but number of moles Ca is 1, Cl is 2. Okay. So, all these things have to be considered in the equation. That is why the notation that we had taken Ni was very important at the very outset. So, half Ci Zi square here sigma is essentially a mean concentration of all the different ions which are present. Now, suppose in a solution if you have CaCl2, NaCl, KCl, these kind of competing ions, okay, over the ion selective electrode in question. So, in that case half Ci Zi square would be, suppose you have 1 mole of KCl present. So, you have 1 concentration of potassium times Zi square, which is 1 square, okay, plus 1 concentration of chlorine plus Zi, which is minus 1 square. So, this is the way you have to keep on computing the mean concentration, divide the whole thing by 2, so that you have an idea of what is the mean concentration of a solution. So, we are going to also solve some examples later on where we will try to find out what this activity coefficient would come in such a situation. Okay. So, from this equation here we try to derive the final form of the equation for activity coefficient in terms of the mean ionic strength, which would be done in the subsequent lecture following this. Thank you.